So today we're going to we're going to look at Haar measure in some detail. Wait, were you here last time? Probably not. Okay, good, because this is like a tutorial on Haar measure, so it's independently going to be okay. So the Haar measure is basically going to see how you so it formalizes how to sample unitaries uniformly at random, right? So this we saw, and it's actually very useful in many different areas. So applications include these are not things I'm very familiar with, but I'll just write them down. So it's useful for tomography, when you're doing random circuit sampling. It's useful for foundations and communication. Also used in machine learning and many body physics and so on. So basically, essentially all areas of quantum information. So quantum many body physics and high energy as well. So it's good to spend some time on trying to understand what this is. So here we are going to basically focus on. So the tutorial is much more detailed, I think, than what we need. So the second section is just going to tell you some notation, which we'll look at in just a moment. Section 3 is going to tell you, what the Haar measure is, and it will introduce moment operators and so on. So this is going to be the focus of today's lecture, moment operators. And next time we'll try to do section 4, which is symmetric and antisymmetric subspaces. Okay, so that's the plan. In the tutorial there are other things as well, so that there's talk of vectorization. I'm just mentioning them in case you're interested in looking at them further. There's the tensor network notation, then there's unitary designs, which some of you might already be familiar with. Then there's approximate unitary designs, and then there are applications. Okay, so these will not cover, but they are in the review. So if you're interested, you can look at them. So that's the thing. Okay, so let's start with the notation. So we're going to use, so it's mostly standard notation. So these are linear operators on CD, Hermitian operators. Hermitian operators on CD. This is identity on CD. They distinguish identity on CD from identity on CD tensor 2 for some reason. It's probably useful in some way. Okay, so that's the slightly unusual notation. U bracket D is the set of unitaries on CD. Right, U dagger U is identity. And finally D, so this is sometimes from 0 to D, but here it's just going to be from 1 to D. Okay, so this is just standard notation. Norms we can probably skip because we haven't really used them, at least we'll not use them today. We use the Hilbert-Schmidt norm. So we'll use AB, HS to mean trace A dagger B, right? That's pretty standard. So the other things maybe we can skip for the moment. Stuff about quantum channels is not needed. Okay, good. So now we can start the section 3 already. So Haar measure and the moment operator. We should put it on silent. And the moment operator. Okay. So we saw this definition already actually, but let's set the notation that they're going to use here. So the Haar measure on the unitary group UT is the unique probability distribution, probability measure, not distribution, which they write as mu sub h, slightly different from what we discussed last time. That is both left and right invariant. Left and right invariant. And the definition was formally that for all integrable functions, f and for all v inside the unitary group D, it holds that integration over the unitary group of u using the Haar measure u. So we saw this before. So what would be the left invariant condition? Right. So v was the arbitrary unitary, so vu, right, d mu h u has to be the same as the same thing on the right, yeah? So v d mu h acting on u. Right, so that was the definition we wrote down, we'd written down last time, and we're just going to assert even now that this is going to be unique. We'll not prove it because that gets deeper in too deep in math for this course. I also don't know the proof, but let's see what the consequences are, assuming that it is unique. Okay. So the informal claim is that for compact groups, so which includes unitary groups, okay, there exists a unique probability measure that is invariant under left and right multiplication. So the statement is more general. Not only is it true for the unitary group, it's true in general for any compact group. That's what the claim is telling us. And since the Haar measure is a measure, it holds that there's normalization, so d mu h u. Oh, sorry, this normalization I'm saying it's positive. So you take any subset of the unitary group and you integrate over it, you're going to get something positive, or non-negative rather. And if you integrate over the entire unitary group, then you should get 1. Right, so this is nothing fancy, it's just standard sanity checks. Okay. Yeah, now the definitions are not going to be too long, so we'll mostly spend time proving things, unlike the previous sections. Okay. So notation. So we use expectation u sampled from mu h f of u So this we had something similar last time as well, right? Fu d mu h on u. Okay, and sometimes I'll even drop this sample from, I'll just write expectation because it'll be clear from the context. And because somebody had asked, I think last time, what the range of f is, or the codomain is. So when f u is matrix valued, expectation is entry wise. Okay. So already with this we can show the following. So we can show that. So we show that unbalanced products of matrices vanish. Okay, so what this means formally is the following. So they show that you take k1, k2 to be natural numbers, okay, and if it holds that k1 is not equal to k2, then expectation of u sampled from the Haar measure using the notation above, u tensor k1 tensor u tensor k2. Star is going to be 0. Okay. So, does anyone see the proof? We just have to use the left-right invariance property. So you basically have to cleverly choose a v that would give you the result. Any guesses on how we could? Basically, this is going to be common all throughout. Like essentially, all the proofs are basically just about picking the right left multiplication or right multiplication.
You just have to like make it negative of the.
Yeah. So you have to pick a v such that you have to add a phase. Yeah. Okay, so very good. So now the idea is that, okay, so the proof is that you replace u with u e to the I pi k1 minus k2, right? Because you'll get multiplied and okay, and of course this doesn't change, right? Doesn't change the value of the integral. Because of the left-right invariance, right? And so you can write u tensor k1 tensor u tensor k2 star is exactly as what was your name again? Arnab. Exactly as Arnab said. So you just show that it's the negative of the same quantity, right? Tensor k2, right? So that completes the proof. Yeah? Tell me, okay, if something doesn't check out or if I've made a mistake somewhere, because okay, so that was a quick warm-up. Now the next proposition is a calculation that we'll use later. Okay, so the following is helpful, is useful later. Okay, so it shows we can replace u with U dagger under Haar integration. Haar integrals. Okay. So what is the star? Yeah. It's just a complex contributor. Sorry, being a bit quick. Okay. So now proposition 3. So for all integrable functions f. So I'm writing the statements slightly informally sometimes because we know what it means. But you can look at the paper for the full formal statements. Okay. So if instead of u you replace it with u dagger, it doesn't change the expectation. Right. So that's the statement. Did I mess up? Everything okay? Okay. Okay, good. So now let's look at this. So how do we prove this? So the idea here is going to be that we're going to show that u dagger as well is left-right invariant. Like this integration is also left-right invariant. Wait, was it this way or the other way? I think it is that, yeah. And because the left-right invariance is unique, we'll be able to argue that it's the same thing, if I remember well. Okay, so they're going to define mu dagger to be the probability measure, which is defined as follows. So integrating over ut, fu d mu dagger u is defined to be the following. So it's basically the same thing, except you do it on u dagger. Okay, so it's just notation. So this is what the measure basically means. This is just the definition. Okay, so we've not done anything very deep. Okay, and now what we're going to do is we're going to argue that this thing is also a Haar measure, so it satisfies left-right invariance, and then from there we'll be able to argue that this must be the same as d mu. Do we have space? We do have space. Okay. Okay, so strategy. Show d mu dagger is also left-right invariant, and because Haar is unique, so we're cheating a little, right? Because we didn't prove that it's unique. We're just assuming that it is. Therefore, mu dagger is the same as d mu. Okay, so let's see.
For example, even if we sample u dagger or u from the same unitary group, why do we need to take some different measure like d mu plus u? Because the group is not changing. So whatever we are sampling, so why do we need to make different measure?
It's just a proof technique. You can probably prove it using a different technique if you like. Here they're just trying to argue that I'm defining a new measure. I can define it in whichever way I want, and then they're trying to argue that this measure is the same as it also has the same property that it's left-right invariant, and therefore you can conclude that from the uniqueness of the Haar measure that these two measures are the same. So whether you integrate using one measure or the other, they're going to give you the same answer, which lets you prove this statement. It's just a proof technique. You don't have to do it. Maybe there's a more clever way of doing it, I don't know. I also learned this like yesterday. So. Alright, so let's start then the proof. So integrate over ut f uv, oh sorry. So suppose that v is some, v be some fixed unitary. Okay, and then fuv of d mu dagger u is the same as integral over ut f u dagger v d mu h u. Okay, so this is just by definition. I plugged in the definition, so I've not done anything very deep here. Now ud of f u dagger v dagger v d mu h u. So this holds because I can write multiply with so I can write multiply u. Actually I left multiplied, so what I'm doing is I'm sending u to vu, right, in the function. So when you apply the dagger it will get flipped, you'll get this. Okay, so invariance of Haar measure under okay, or Haar integral, actually maybe not the measure of Haar integral. Okay, and then this becomes what? It becomes fu dagger d mu u. Okay, and this becomes the same as u fu d mu dagger u. Right?
The Haar measure was correct. Invariance of Haar measure. Because like you can always substitute something like instead of the u you can substitute like vu, and the d mu of uv is same as like d mu of u.
Yeah, but this statement is also correct because I only care about the integral. Like the value of the integral is unchanged. That's what I was trying to say. But strictly speaking, you might be correct. I don't actually remember exactly how they formalize it. All I mean is that what we said in the definition, that you swap f. So yeah, if they said measure, maybe you can use measure. Just have some insecurities. Okay, good. Okay, so this step is fine. Yeah. All I did was I swapped u with vu. Right? Because I can view the whole thing as just a function of u, right? And then is that okay? This step is v dagger v, so it's identity because it's unitary. So this is fine. And then this is just the definition of this object that we defined, right? So what does this show? It shows us that you write multiply or you don't. It gives you the same value, right? And then you can repeat the argument for the other side, and so then this would give you that. It basically establishes the strategy, right? That it's both left and right invariant, and so therefore it must be the same as the Haar measure. Okay. Okay, so now we're going to introduce a new object. So a quantity that plays an important role. In our analysis. Is called the kth moment operator. Okay, and this is going to be sort of natural. So k is a natural number, right? Okay, so what is the quantity? The quantity is the following. So fix a probability measure mu h, okay. Then the kth moment operator, oh shoot, I'm not supposed to write cursive. Moment operator is given by the following. So you have m, k is the kth moment operator relative to the measure that you defined. So we're using the Haar measure. So it takes operators from CD tensor k to CD tensor k. Okay, and is defined as follows. Should I? Okay. So this is your sample U from the Haar measure. You multiply k copies of the unitary, and then you do the dagger. So you're basically conjugating by k copies of the unitary k. Okay, and this is for all O in CDK. All linear operators acting on CDK. Okay, so that's just the definition. Why it is interesting will become clear as we prove more results. The definition is fine, right? Like it's just straightforward. You're multiplying and you're conjugating by UK. Okay, so this says that by characterizing the moment operators and computing its matrix elements, one can explicitly, and we'll see this in more detail, one can explicitly evaluate Haar integrals. Okay, so the example they give somehow in the text is, or sorry, in the paper is that, you take the operator to be I1 to IK. Okay, so it's just a rank 1 operator. Okay, and all of these are basically in D, right? All of these entries are in D. Okay, then L1 to LK acting on the Haar measure mu h U dagger tensor k m1 to mk would just be L1 I1 LK IK U star M1 J1 U star MK JK. Okay, where MK JK are also, these are also in belong to D, right? So what that tells us is that so basically you're going to encounter objects like this often. So even when you define pseudo-random unitaries, you're going to have the the operation multiplied by UK dagger. So for pseudo-random states, it'll probably be some fixed 0 state, and then you're multiplying it by the same unitary, right? So you're given many copies of the Haar random state, and so on, and you're computing expectations, and this is what the expression turns out to be. Okay, and then to compute these kinds of expressions, we need, or to give the characterization of moment operators. We need kth order commutants. Kth order commutants. So commutants are of a set of matrices. Basically, just a bunch of operators that commute with all elements of S tensored K. So by this, what I mean is the following. So definition 5. So a commutant is defined as you're first given a set of operators from LCD, so it's a subset, and the kth order commutant is the following object. Commutant Sk is defined as A's in the set of all linear operators on CD tensor K, okay, such that A commutes with K copies of B for all B in the set S. Okay, so you basically take an element from the set S, you make K tensors, okay. Your operator must commute with such an object for every B in the set. Okay, if that happens, then that A is in the commutant of S. Okay, that's the definition. Okay. So at the moment, it's just a bunch of strange definitions, and we don't really fully understand what's going on. But it seems to have a lot of. It has a connection with the symmetric group and all these things, right, that we saw last time as well. So we'll try to make some progress towards proving this. So the first note here is that the commutant is a vector space, right? So the commutant, let's just write it explicitly, commutant is a vector space. Oh, was there a question? Did something? Oh.
Definition looked similar to the normalizer of a stabilizer.
Yeah, probably. I forget the exact definition. I think the difference is that you're doing tensor K. I think that's maybe the only difference. Because normally you just take the element of the group and then you construct it. Here you have to take like K tensor, so it's a bit more specific because of that. Okay, and okay, so it's easy to see that it's a vector space, right? Because you can take any two elements and then they will also satisfy the same condition. Okay, good. So now we're going to do something more interesting. So now we see that the moment operator is an orthogonal projector onto the commutant of the unitary group. Okay, which is so the commutant of the unitary group, by this we mean you take the set S to be UT, right? So you construct, you take the set of all unitaries, you look at all operators that commute with U tensor K for all U's, and that would give you the set. Okay, and this is with respect to the Hilbert-Schmidt norm. Okay. So before we establish this, we have a little. Okay. So to this end, we first show the following lemma. So we first show the following lemma. What is the lemma? Let's write it down. So, lemma 6 says following. So this is some properties of the moment operator. So let's do that. Okay. So the moment operator M K mu H, which was defined as U sampled from mu H, U tensor K, some object here, U dagger tensor K. Did I put the dagger over there? Yeah, I did. Okay, good. So you take the moment operator. Okay, so this has the following properties. Has the properties. Okay. The first one is that it's linear, it's trace preserving, and self-adjoint with respect to the Hilbert-Schmidt norm. Okay, let's write this one. Second is that for all A in CD tensor K, the moment operator after being acted upon, after acting on A is going to be in the commutant of the unitary group. Okay, and the third is if A is already in the commutant of the unitary group, then the moment operator acting on A gives you, it leaves it unchanged, so it gives you A back. Okay, so these are relatively simple. Let's try to prove them. Okay, so linearity is immediate, right? Because just by the way it's defined, it's conjugation and expectation, so all of those things are linear, so it's going to be okay. Trace preserving is also immediate, right? Because yeah, trace preserving is fine because yeah, exactly. Okay, so cyclicity of trace would give you dagger U disappears, and then you have the initial quantity, so the trace is the same. And expectation, of course, you can swap the order, so that's fine. And so okay, so the self-adjoint part is what we want to show now. Okay, so number one. So we want to show. So okay, so it suffices. Okay, remains to show that M. So I'm not going to write. I'll just write M sub K, okay, because it's a bit quicker than writing mu sub H every time. So we want to show that the Hilbert-Schmidt inner product with all B's and all A's is the following, right? So you want to show that it's a self-retrieving. Okay, so this quantity one can write as what? One can write it as mk dagger A 1B, right? And then one can expand it. So expectation over U is always sampled from the Haar distribution. Okay, so we just apply the definition. The definition says you take U dagger, conjugate with UK dagger. Okay. Okay, and then let's swap it. So let's write it as trace. A dagger, U dagger tensor K, B, U tensor K, expectation over U. I can do that, right? Because the trace is cyclic, so I can take this U, take it to the other side. Yeah, and then just expectation, so not done anything very complicated. And then this is trace of A dagger and just M acting on B. And we also use the property that you can swap U dagger with U, right, which we proved in the proposition earlier. Yeah? Is that okay? Something wrong? Okay. Okay, so we used, so here we used proposition, so in this last step we used proposition 3, okay, so which was saying that U dagger and U can be swapped under the Haar measure. Okay, so that establishes the first one, so this is done. So now let's look at the second property. Okay, so the second property is that we want to establish that M acting on A is inside the commutant. So okay, so this object M acting on A is what? So let's suppose we write V mk, yeah, maybe let's say, okay, so mk is in the commutant. Okay, so this thing I'm abbreviating as just com. Okay, so this is being used to define com. Okay, so so mka in com is equivalent to saying that you apply k copies of an arbitrary unitary v and it leaves mk invariant, right? So these two conditions are equivalent. This is fine. I've just used the definition of what the commutant is, right? So an object is in the commutant if you conjugate it with v and it's the same. I think the commutant we wrote it as that it commutes, but it's equivalent, like so. Yeah, right. U a equal to 0 is equivalent to U dagger equals A, right? Because this is fine, right? It's very basic. So I'm using that fact. Okay, so we have this, and now what we can do is what did I do now? Okay, I did exactly the same step. Okay, so this is equivalent to UK mka is the same as mka v tensor k for all v in ut. Okay, so it's just this step that I mentioned. Okay, and then what did I do? Then okay, so now here's a note. The note says that v tensor k acting on mka. Okay, so this is basically the burden. This is what I want to prove. I haven't proved anything. This is just so I'm starting from the left hand side and trying to argue that it's actually equal. So let's start with this object, okay, and expand and write down the definition of mk. So what is the definition of mk? It's that expectation over u tensor k, a u dagger tensor k, right? So far I've just written the definition, and what this tells us is that I can write the following. So I can take the expectation outside, I can write v tensor k, okay, and then I can write v dagger tensor k, u tensor k, a u dagger tensor k, and v tensor k. Okay, so why can I do this? Because I can always send u to some left multiply, right multiply, and so on. So those are fine. So I can send u to v dagger u, right? And the integral, the expectation doesn't change. So I just did that and pulled out the trace. So and then this thing disappears, right? And then you're left with essentially mk a being the same. So this part becomes mka, and then you have vk left, right? But this is exactly what we wanted to show, right? It's true for all unitaries. So that tells us so this establishes that you start regardless of which a you start with, once you apply m, it's going to start commuting with all unitaries u tensor k, conjugation with unitaries. Okay. And then we have the last part. So the last part is now kind of easy, right? Because so if A already belongs to something that commutes with the unitaries, right? What is the action of M? M just conjugates it with the unitaries, right? But it already commutes with the unitaries, so the unitaries will not do anything, right? So just to be sure everyone's with me. I mean, this is very elementary things. It's just a bunch of definitions, so you have to keep track of what's happening. But so this basically means that u tensor k acting on a u dagger tensor k is the same as a, right? So this is what it means for all unitaries, and then expectation over u tensor k, a u dagger tensor k is going to be exactly a, right? Because it commutes, and this object was m k acting on a, right? So that's fine. So that essentially completes the three properties we wanted to establish of the moment operator. Okay, so now we have the theorem that we mentioned in the story earlier. So project onto the commutant. Okay. So this says the moment operator so in the theorem I'll write the proper notation. So which recall was just uk dagger tensor u dagger tensor k, right, and expectation over u sampled from mu h. Okay. Is the orthogonal projector onto commutant ut k, which we define as com, with respect to the Hilbert-Schmidt norm. Okay, and in particular, suppose P1 to P dimension of com, okay, be an orthonormal basis, orthonormal of com. Okay, so you pick an orthonormal basis here, and you take O to be any linear operator acting on CD tensor K. Okay. Then it holds that any operator O, when acted upon by the moment, what is it, the moment operator, would be expressible in the following form. It's dimension of com PIOHS, Hilbert-Schmidt inner product PI. Okay, so that's the statement. So it's not saying too much, right? Because we already claimed that this thing is projecting onto that space, and we just wrote down the orthogonal projectors for that space. So obviously any object in that space can be written as a linear combination of these objects, right? So that's all we are saying, that the moment operator acting on whichever thing can be written as a linear combination. Okay, it's nothing very deep that's happening. So let's prove it. And given the lemma, I think it's kind of straightforward as well. So let's do it. Okay. So here's the proof. So you start by extending, so you extend the orthonormal basis of the commutant to span LCD K, right? Because the commutant is a subset, right, of LCDK. So what we are going to do is we're just going to extend the basis. So the basis is now going to be, so initially we had until the dimension of com, right? So now we're going to introduce more projectors. Yeah, so this thing was defined to be V. Okay. So I'm writing V like this because sometimes my small v and capital V get conflated. So yeah. Okay. So that's the these are the projectors. Okay. And so now one can write M, the moment operator acting on some projector, or sorry, some operator O, as follows, right? So one can write it in terms of the Hilbert-Schmidt inner product and the corresponding projector. So this gives you the component, that's the projector. And now since it's spanning the entire operator space, you can always do this. It's true in general. But one can split it, right, into two parts. So one can split it into the part with the commutant and the part with the space outside the commutant, right, which is spanned by this part. It's exactly the same, MKO. Okay. Now the lemma tells us that, because we already established that any the moment operator acting on A is always only going to have support within the commutant. So it's evident that this part has to be 0 because you cannot have any support on that side. So that is kind of trivial, and it remains to show the the exact form, right? Because I kind of removed the M from here, right? So that's the only little thing that needs to be done because there's an M here. So, but that's also kind of straightforward because we established that M is what was it, self-adjoint, exactly, thank you. So it's self-adjoint, right? So we can, so these two are equal, and then from this property here, right, we know that since, so P is already within commutant, right, because it was one of the vectors, and we saw that any operator which is already in the commutant is unaffected by the moment operator, right? So this thing is also going to be the same as Pi, right? And so that gives you the characterization. Okay. Yeah, maybe I can just write because Pi is in the commutant and lemma 6 point, what was it, 3. Okay, and here we used, what did we use here? Oh yeah, and we used from here to here we used self-adjoint MK under Hilbert-Schmidt. Okay. So that completes this part of the proof. Okay, so now so we just saw how the moment operator, right? Let's just saw how M sub k is closely related to the commutant, right? So commutant with respect to, commutant of the unitary group. Maybe that's probably the better way to write. Okay. So here's an interesting observation. So a set of operations that, okay, and what was this, right? This was basically operators commuting with U tensor k, right? That's essentially what the commutant was. So a set of operations that commute with U tensor k is the permutation among tensors, right? Okay. Actually, it's true not just for unitaries, right? It can be any matrix, and this would be true. But let's do it formally. Okay. So we define permutation operators, and then we'll look at why permutation operators are interesting for what we're trying to do. Okay. So the definition of permutation operator. This is something we also did, I think, last time, but let's get the notation straight. Okay, so you're given some permutation pi in Sk. Okay, Sk is the symmetric group, which is just the set of permutations as far as we're concerned, because we're on finite sets. Okay, so we define the permutation matrix Vd pi as follows. Okay, so we define this as, so basically you define it using the action. I mean, that's what they do, but it's equivalent, so it's not a problem. So psi1 tensor, we didn't define it like this actually last time. We defined it in an equivalent way, but it's all the same. So if you have any tensor product like this, you're going to write it as psi pi inverse. I still don't know why they use inverse instead of the direct permutation. It's not become evident in any of the proofs I've looked at. and this has to be true for all psi in CD. Right? It's just the definition, nothing very deep so far. Okay. So some elementary observations. So Vd of sigma and Vd of pi is going to be Vd of sigma pi. Okay. And I think maybe this is why they write it as inverse, because otherwise it would be pi sigma. So maybe that's the reason. Okay, then Vd of pi inverse is the same as Vd dagger of pi. Right, that's kind of elementary. Just flip the order. And then Vd of pi can be written as sum over I1 to Ik, right, where each element is in O1 to D, and then I pi inverse 1 I pi inverse k. Let's start with I1 to Ik. Sorry, yeah, I ran out of space, but this is equivalent, right? Because so this one way follows because it's true for all psi I, so it's in particular true for these, and the other way is it's a complete basis, so you can do it. So it's not a big problem. What else? Yes, and then the final simple observation is that if you have A1 tensor AK Vd dagger pi, this is just going to be the same as, well, basically just permutes these objects, right? Tensor A pi inverse k. Okay, and yeah, this is true for all A in CD. Okay, so far it's expected stuff, relatively straightforward, but here's a very surprising fact, which we will not actually prove in full generality, but we'll prove either today or next time, at least in some special cases. So it turns out that permutation operators so we know that they certainly satisfy, they commute with all U tensor K, so they certainly are contained in the commutant of the unitary group. It turns out that they actually span it. So these operators characterize all possible matrices in the commutant. Okay, and this is called the Shor-Weil duality, which I don't know much about, certainly not in this context. Okay, so let me write the theorem. Okay, so the theorem says the following. Theorem 9, Shor-Weil duality. Okay. So yeah, I'm not writing it in words. It basically just says that the commutant of U D comma K is the same as the span of Vd on pi for pi in Sk, the symmetric group. Okay, so the containment. So one direction is easy, but the other direction is not obvious. At least not to me. Maybe some of you can see a simpler proof. So Okay. So let's at least do the simple side. So general proof, like I said, we'll skip for now. K equal to 1 and k equal to 2 we'll do later. Okay. And so k equal to 1 is what you were saying, right? It's identity because of the, well, last time we actually just asserted this show while duality, and then we said that for k equals 1 it would be identity. And for k equal to 2 it turns out it's just a sum of identity plus swap. And then we'll see the, hopefully we'll see the proof. Probably not today, but well, let's see. Okay. And the other thing is, yeah, so okay, and so now we're going to basically see that, so it's easy to see that the span of VD pi in SK is contained in, so this direction is trivial essentially, so let's do the trivial thing. Okay, so observe that VD acting on pi U tensor k acting on psi 1 tensor I psi k, right? So this one can write as, right, because maybe I should say, so it suffices to show that VD pi and U tensor k commute, right? That's just the definition of the commutant. So that's what I'm trying to do. So I'm applying VD pi, you know, in this order first, and then I'll show that it's the same as the other order. So I'm just applying it on some arbitrary vector, and you can probably already see where this is going, right? Because so I can apply it to each U psi 1 tensor U psi k, right? And crucially, they are the same unitaries, right? So the permutation is basically just going to, you know, you can call these phi i's if you want, phi 1, whatever, phi k, and then we can just use the definition of the permutation. So this would give you what? It would give you, so it would give you, so yeah, maybe let's just write it. So this would give you phi of pi inverse 1 tensor phi of pi inverse k, right? So that's fine. And what that would mean is that you basically just have u of, let's say psi pi inverse 1, just substituting it back, right? I'm not doing anything. Psi pi inverse k, right? And this is just the same as U tensor k acting on, apply the permutation on these things. So what was it called? VD pi. Right? But that's what we wanted to show, right? That you can swap the order. And we did not use the fact that it's unitary actually. So this holds for, as long as you're applying the same operator on all the kets, it doesn't really make a difference. Okay. So that is good. Now there are some more remarks. Okay, so it's important to note that even though permutation matrices, right, using the Schur-Weil duality, the theorem statement, right, so even though the permutation matrices form a basis for the commutant, right, UDK. They are not orthonormal in the Hilbert-Schmidt inner product. Okay. So what that means is that, you know, we cannot, as a consequence, apply the nice characterization that we had from cannot apply theorem 7 directly, right? Because theorem 7 was saying that you can just take inner products with the Hilbert-Schmidt inner product with the operators that are spanning it, but we cannot quite use it. So here we'll have to develop a slightly different approach. So nevertheless, there is an alternate approach. To evaluate moment operators. And therefore, integrals on Haar measures. Okay. So that's the story. So now let's write down the, yeah, probably the last theorem. We'll actually may be able to do a bit more. Let's see. Okay, so now we have theorem 10, which is computing moments. Okay, so let O be a linear operator on CD tensor K. Okay. Then it's on. Okay, sorry. Then the moment operator can be expressed as a linear combination so this part is not surprising, right? This is just following from the theorem, combination of permutation operators. Okay. So the statement is the following, say of K, O, right? So recall this was just expectation over U tensor K acting on O, U dagger tensor K. Right, and this thing is the same as sum over pi in the symmetric group, some coefficient that is indexed by pi for the operator O, and then VD pi. Just an orthonormal, almost like orthonormal basis, but here it's just a linear combination, so the coefficients are given by C pi K. Okay. And here's the non-trivial part of the theorem, which says that where the coefficient C pi O can be computed by solving K factorial equations. And what is the equation system? So trace of V dagger sigma acting on O is the same as you sum over all permutations, the coefficient, and then trace VD dagger sigma VD pi. Okay, so this is for all sigma in SK. Okay, and finally, the system has at least one solution. Okay. So yeah, the proof is not too long. Let's quickly do it. The statement is fine, right? Nothing very deep happening. Okay, so let's label the equation. So let's call this equation 30. Let's call this 31. Okay. So equation 30 essentially is sort of a variance proof. So equation 30 just follows from lemma 6.2, right, which said that mk of any operator is going to be in the commutant, right? So that's the previous statement, and sure while duality. Okay, which says that the commutant is a span of permutations, right? That's what we had. Okay, so now to get equation 31, we proceed as follows. So let's write down the expectation of V dagger on sigma u tensor k O u dagger tensor k. Okay, so we're basically just starting with this equation, but we left multiplied it with a V dagger t, right? So you get what? Sorry, this is just a complex number, so it doesn't really matter. It's not zero, it's V dagger d sigma Vd acting on pi. Okay, and because this is a permutation, right, and we saw that permutations they'll commute with all u's, right? We just saw that a moment ago. So one can write this as follows. So one can write it as u tensor k Vd dagger sigma O u dagger tensor k, and here you can now take the trace, and the trace, the u dagger will disappear, right, and you'll be left with Vd sigma O is the same as C pi O trace V dagger d on V dagger sigma inverse pi, right? That's the okay. And the claim that there exists a solution just follows from the fact that the Schur-Weil duality, that the space is spanned by permutation, so there has to be a solution. Otherwise, it doesn't make sense. Okay. So I think it's a good point to. Let's see if there's something small I can tell you. Yeah, so there's like some small remarks, maybe we can write them quickly. So there are some remarks, actually maybe I'll write them next time. For now I'll leave you with this proposition. You can think about it, how you would prove it, but we'll prove it next time, okay? So for pi in pi a permutation, the permutation matrices V d pi are linearly independent if k is at most t, and linearly dependent if k is greater than t. Yeah, the proof is kind of cute, but Yeah, I think maybe let's stop here because it would be a bit more difficult.